welcome to this webcast about the AnyBody model library updates. My name is Søren, and the outline for today is a short introduction to the repository. Then I'll go through some of the body models already existing, and I'll look into details of some of the new developments in this release of the repository. And there will be some demos showing some of these new models and facilities. Then we'll look at the application currently available and some of the new applications, and there will be a short slide about the new license terms, and I'll show you how to obtain these models. So with me today, we have a host here. It's Kasper Gerner Mikkelsen, and Sylvain is on the panel list. He's the one that will answer the questions if you have questions while the presentation is running. And actually, you can ask the questions while the presentation is going on by clicking this question mark here in your lower right corner of the screen, and then this will launch this panel here. And you can type in your question, and then when you send it, then please remember to send it to host, presenter, and panelist. Then this will ensure that the right person sees it. And you should also notice that sometimes the answers doesn't display next to the question in the Q&A box. You may have to scroll up a bit and down to see the answer to your question. But please just ask questions along. But after the presentation, I'll also answer questions if there are more questions, of course. Okay. The repository, we have a different approach than normal, we think. I mean, most research groups, they start with a problem and build a model to solve this particular problem. And we want to build general models which can give information about a number of yet unknown problems. So our goal is to develop general details models which can predict muscle and ligament and reaction forces for a given motion and load. And we want to enable sharing of these models, and we want to give the opportunity to scrutinize and improve these models by other research groups and individuals. And for this purpose, actually, we have developed now a new community site named AnyScript.org. I'll also show this later at the end of the presentation, but this is all done to facilitate this sharing of the models. This is an overview of the repository structure. With this current release, the focus areas of the repository has been to increase the user-friendliness and making it easier to get access to the most used output, and also to be able to define new models in a smarter way. And the structure of the repository remains the same as it has been previously. It has a very strong separation between the application models and the body models. So it has basically these two branches. It has the application branch, which is all the examples of the different models. It can be a bicycle rider, a gait model, and so forth. Whereas we have the body parts completely separated and divided in different subdirectories. And so this repository I'm talking about today is running with the newest version of AnyBody version 4, which has been released today. But now we will go briefly through through the body models that is currently existing, and then we'll switch to the new stuff. But first, we'll talk about the structure of the body parts. Basically, the body parts are made with a modular block building technique, which makes it easy to change and connect different body parts that has been developed. So the philosophy is that when building, for example, a leg model, this model should be entirely self-contained. It should contain all the nodes that it will need to maybe to insert on the pelvis for its muscles attachment points. So it really is, blocks that comes and that are connected together. But each body has to know all its details about itself. It's not sort of spread out through the other body parts. So we can also now in this case we have two leg models which can be so it's free of choice to use to shift between these two models, and since they have been made in this way, you can just shift between them because they all know how to attach to the pelvis. And most importantly, of course, is that these body parts, they do not contain any motion drivers. They do not know, I mean, what to do with themselves. It's really just like a jumping jack model without any strings attached. So the drivers are applied in the application where you actually make use of the body parts. So if you look at the structure of the body repository, it is, if you look in the AU human folder, it's the Aalborg University folder, it has these items. If you look at the first one, it's an arm model. There has been some modification in this release related to the pronation supination joint, which has been slightly modified. And there are also some addition of output available in this arm folder now. So looking at the leg, it's mainly, most changes are with regard to getting easier access to the output. Then there's the leg TD, it's a Twente leg model, and it's entirely, it's new in this repository. And then there's the trunk, which has been, that's also been made easier to get access to some of the output. And some additional modules has been added, which are spanning the joint between L1 and T12, which enabled us to remove a reaction force which was previously present in the model because of lack of muscles to carry this reaction. But this has been removed now. If you're looking at the trunk and neck, it's mainly it's the same modification as in the trunk, but it's also containing this additional output. When looking at the body models, there has been addition of, so it's now possible to do something we have named generic body models. I'll talk more about this later. In the scaling folder, there are some new additions related to the scaling of Twente lower extremity model. So this has been so part of this work has really been to make this model scalable in the normal way that the other models can do it. So if you look at the spine model, in the cervical region, it has 7 vertebrae, and it has 136 muscle facets, and it has 3 spherical joints from T1 to T2. And it has 1 degree of freedom universal joint from C2 to the head. And if you're more interested in details about this model, there's this article to refer to. The thoracic region is under construction. Looking at the lumbar region, we have there are 5 vertebrae and there are 188 muscle facets, and it has an intra-abdominal pressure model actually implemented that are, it's basically like a balloon that is retruded just like any other models, any other muscle by the recruitment algorithm. So if there is a need of this intra-abdominal pressure, it will do it. Otherwise, it's not active. Yeah, and these joints in the lumbar region are also made as spherical joints. And there are 2 articles related to this lumbar model. Looking at the shoulder, it has 118 muscle facets on each side, and the wrapping of the muscles are done by contact mechanics. So the muscles are really wrapping on spheres and ellipsoids and cylinders that has been fitted to the bones. In the glenohumeral joint, it's basically in terms of kinematics, it's done as a spherical joint. But in terms of reactions, it's not like that. Then these reactions has been the normal reaction in the spherical joint has been removed and replaced by a contact criterion that ensures that the resultant force of this joint always will point inside the glenoid cavity. Yeah, so it will really recruit the muscles around this shoulder joint differently to always have this reaction force inside the cavity. This reaction force simply cannot go outside the cavity. So it cannot dislocate in that sense. Looking at the joints, we have the acromioclavicular joint here. It's a spherical joint. We have the sternoclavicular joint here also as a spherical joint. And as I said, we have the linear one as well as the spherical joint in terms of kinematics. Then we have a 1D constraint from this bony landmark TS and AI acting to the thorax, and it's the thorax is kinematically here modeled as an ellipsoid that has been fitted to the rib cage, which means that this sort of controls the scapular thoracic gliding plane. Yeah, and lots of this, anatomical information originates from the Dutch shoulder group, and mainly it's these three articles that should be referred to. Then there's a mandible model. It's based on a CT scan of the normal face of a 30-year-old male. It has 24 heel-type muscles acting, and the mandible joint is modeled with 4 degrees of freedom. And again, there's the data originates from this article, and there is Mark Pesset, who developed the model, has a paper in the Journal of Biomechanics, which can be seen here, which is describing this model in detail. Then there's the new Twente low extremity model. This model has actually been released previously as a standalone model, and the model is based on the recently published morphological consistent anatomical dataset on muscle and joint parameters. And this model is now available in combination with any other body part in the repository. So this is part of the work that has been done, is that really to make this model scalable with the different scaling laws, and make sure that it acts in a good way together with the other body parts. So you can really shift freely between the different leg models now. And here in the bottom there is a reference to a paper where this data is described. So it's really it's a very comprehensive and consistent data set from one donor. It has 55 muscles divided into 159 vessels per leg, and each leg has 7 degrees of freedom. It has 3 in the hip. It has a revolute joint in the knee, but it has the patella as well, and it has 2 degrees of freedom in the ankle region. And there are some new applications in the repository which are now running with this model. It's a Gait application named GaitUniMiamiTD. Actually, it's an application which it also existed in previous releases of repository, but now it has been reworked and re-optimized to run with this leg model. And there's another variation of that model. It's running only with the right leg, which is this second mentioned model here. But if you need more details on how this model has been developed and so forth, there is also there has been a webcast previously named A Detailed Low Extremity Model. It was by Sebastian Dendorfer in August last year. And there's a link for it here. I know this link is a bit long, but you will get a copy of this slide, so you will be able to see this link afterwards when you get this copy. All these models, they are of course scalable. And I'll briefly go through the different options for the scaling facilities in the system, in the models. So all models are scalable in size, and it's really not a simple task, since it involves changing literally thousands of parameters. And these properties like the mass and inertia of the segments, it's the geometry of the muscle. It's not just insertion points and attachment points. It's also the joint centers and the wrapping surfaces attached to the bones. It's muscle parameters and the wrapping surfaces. And the scaling procedure is implemented in a generic manner that allows the user to define the scaling laws. So actually, there is in the body model, in the body directory of the repository, there is a folder named scaling, and in this scaling folder basically the scaling laws has been defined. So the body parts themselves, they will not know how to scale them. This is something that comes defined from the outside. They have facilities built into them that allows them to be scaled, but the exact way of doing this is sort of controlled from the outside. There are different scaling scenarios. We can scale for an overall population level. If you want to investigate economic compatibility for a broad range of the population, or it can be based on a chromatic database, or it could be on an individual level where sports biomechanics, where you're looking into, for example, sports biomechanics for a particular athlete, or it could be a gait analysis of a particular individual. And of course, it can also be purpose-specific modeling based on scans, ultrasound data, and similar. And this actually, when building a new gait model like the Twente model, it's really what is done here. It's really a perfect specific modeling based on an anatomical data set with exact 3D coordinates. But of course, now this Twente model has been made scalable, so you can scale it to any other size if you like. Yeah, and this detail level has always been possible because AnyBody models are entirely accessible. You have access to all the entire model definition. It's not a scaling that is hidden away in the system. It's defined in the models. So how is a segment defined? If you look at the various properties that have to go into the scaling, we look at the segment first. It really is it's a geometry. It's a point cloud of nodes. It's some mass properties of the segments. These small balls here, I should say, is really nodes, attachment points for the muscles and so forth that belongs to the segments. If you look at the muscle, how it's defined, then there's a geometry, of course. It's origin insertion points. It's a strength, and of course it's also the wrapping surfaces that it may wrap on. And the way that these wrapping surfaces has been added to these models is that they have been defined through a number of nodes. So, for example, if we want to define a cylinder, we simply define a node defining one end of the cylinder, another node the other end, and a third node defining its radius. So these three nodes, no matter how they are moved around in space, they will always be able to control the size and orientation of this cylinder. So this is how these wrapping surfaces will have been implemented in a sort of parametric way, controlled through nodes. Because nodes, we will always know how to scale a node. Because nodes, for all of the nodes, we are applying a scaling law, scaling modification. We're doing some, let me explain. We have the original point here, P, which could be the coordinates of the node, and then we are adding a translation vector to this, and we are multiplying it, the node on a scaling matrix. And the different scaling laws, by doing this, we end up with a scale point, and the different scaling laws would have different S matrices and translation vectors. But the way that it's done in the body models is always through this kind of equation. And then the scaling laws are really just changing those scaling matrix and the translation vectors. Yeah. So different choices of S and T lead to different scaling laws. So the different scaling laws currently available is uniform scaling, which is scaling equally with the same factor in all directions of the segments. And this does actually not seem to fit very well with empirical data. Then there's the length mass fat scaling. Length mass scaling, which is scaling the length of the longitudinal dimension of the bone and its width to obtain the certain length of the bone and to obtain the mass of the bone. And then there is the length mass fat scaling, which is where the idea to take into account the fat percentage. And this can be, the fat percentage can be estimated from the body mass index, or it can be measured. So all the scaling is implemented into the models and not in the system. So it's accessible to all of you, and it can be modified by the user. And if you don't like these scaling methods, you can define your own. and the body models will know what to do with those as long as it's fulfilling this you can define the law as a translation vector and a scaling matrix. Then the body models will know how to deal with them. In this new release of the repository, we have created something we have named this generic body models, and it enables the user easily to define the desired combination of the body parts that he may need for his application. And it's in contrast to a pre-selected collection of body parts. In the previous releases of the repository, we have there could be a body model named, for example, full body model, and it will take it will form a full body model. But in case, for example, that you want to have the full body model, but only with the right leg or the left leg for some reason, then this was something that you had to. Then you actually basically have to collect this on your own, and this would require you to write quite a few lines, sort of, to do this. But with this new setup, this has been made much easier. And actually, if we start counting on the number of different combinations that is actually possible, number of ways that you can combine the body parts and the muscle models, there are actually more than 3,000 possible combinations. So it's of course not possible for the developers of the repository to do all of them. It doesn't make sense. So, for example, if you look for the arm, it comes in 3 different versions. It has one version with moment-generating muscles in the joints, so no real muscles. Then it has a version with constant strength muscles and with 3-element hillside muscles. And it's the same for all the body parts mainly. And again, then on top of this, there are different scaling laws that will make them act differently. Out of the 4 different laws here. So combining all these parts, and also, if you want to have the right leg and not the left leg and so forth, makes really a lot of combinations. But this new generic setup allows you to define this easily. So this is an example of how this is defined. In this new version 4, it's possible to do define statements like this. So there's a define statement here saying that this variable trunk here is equal 1, which means now that we want to have the trunk in the model. And then there's a second one down here saying that the trunk symbol muscles is also 1, which means that we want to have the constant strength muscles applied to this trunk. And then further down here there is a define statement, right arm 1, meaning that we have a right arm initially just with the joint moment generating muscles, but then since we have ticked off this right arm symbol muscles here to be 1, then this arm here are now equipped with the constant strength muscles. But I'll show you a demo of this in a short while. Another improvement of the new repository is that we have made a new folder available in all the body models that contains selected output. Any body models, they can generate a lot of output, and it can be overwhelming and difficult to find the exact output that you would need, especially if you're a new user. So these new body models, they come automatically with a folder named selected output, which contains sort of the most used output. It contains reaction forces from each joint with explanations on their directions and a reference frame that explaining the way that they have been measured. They come with muscle envelope curves for each limb, so you can actually see for each limb. As a general system facility, you have always the option to see sort of at any time step what is the maximum activated muscle in the model. It will give you sort of a curve where all muscles will always stay below. All muscles activations will always stay below this curve, and this curve is a good measure for ergonomic design problems. But it has not been possible before sort of to see this specifically for a certain limb. So, for example, if you have the suspicion that a certain arm is overloaded, then you now have the option to see the envelope just for this right arm, not sort of having it combined with activations of the right leg, if that is in the model 2. So you can really see it for each limb separately. Secondly, then the last thing that is there now is that there's a summation of the moments that the muscle they generate around a certain degree of freedom. So, for example, if you're running a bicycle model, you want to see how much moment do the muscles spanning the knee actually produce around the knee. Then you can actually now sort of see this in the graph that all these muscles spanning the knee, they collectively produce this amount of moment around this degree of freedom. Yeah, so it can be very useful sort of to understand your model and how the load is distributed between the different degrees of freedom. So I'll try to make a demo of some of this. First, the first model I will open up is a model in the repository named standing model scaling display. So I will pick the main file and open it. Just get rid of this old model here and press this icon here to have it loaded. Basically, this model is created it's a standing model, but it's mainly created sort of to illustrate different ways of scaling the model. It has no muscle. It's not equipped with muscles. This particular version that I'm running now, so it runs. It goes fairly fast. So yeah. So I should also say that this version of the system I'm running now is actually the new version 4. So one of the main differences that you will see now is the model view. It's actually it's entirely new, and we think that it's very much improved to previously. And one of the things that it can do is that it's actually clickable. So you can click on the objects and get a description of what you have clicked on and where it's exactly constructed in the script. So you can easily sort of directly go to where it's defined. And you can do this for all objects, including muscles and so forth. All visible objects are clickable. But this is not what I'm going to talk about more now. If we look at this section here in the main file, we see here that we have included this file here that gives us the full body model in a version with no muscles. And then down here we can see that we are currently running. Here we have a number of scaling laws. And basically there are these, if you look here at this first line here, there is the scaling uniform. It's the one that scales equally in all directions. And then the second one here is the scaling length mass set, the scaling length mass, and the last one here is the scaling length mass set. And all these three scaling laws, you can only have one of these active at the time. And together with one of these scaling laws, you would also need to have a definition of the segment length. So, for example, this could be this AnyMan file here, which contains here in the bottom you will see that there's a folder here named intro segment length, which defines that the tile length is this size. And in this version here, the tile length means that it's a length from the hip joint to the knee center, to the knee joint center. So all these lengths here are really joint-to-joint distances. And sometimes if you're trying to replicate a certain subject and so forth, this is not so easy to deal with. You would rather have the option to input some external measures that you can actually measure on the guy, which is difficult, of course, with joint-to-joint centers distances. So for this purpose, we have made a variation of these three laws here. And the only difference being that they're doing the same scaling, but it's based on stuff that you can actually measure outside the body. So it's based on bony landmark locations. So if you know your bony landmark locations, you can scale the guy. So we could try to change this person here. So we have this we have loaded this scanning law. This is called scanning length mask set external, and we have this file down here, AnyMan external. So it's a file containing dimensions of the die. So for example, if you look at the tie length here, it's saying that it's 45.5 centimeter, and the measure is from the top to canter to the epicondylus on the lateral along the tie. So we could, for example, try to make this 10 centimeters longer and see how the model changes. So you see the ties got much longer. If, for example, we didn't want to scale the model in this way, but we had only the height of the die, and so we could calculate the percentile that he would belong to this person. We could choose this file here, which is called AnyMan external percentile, and here we can simply just type in the percentile of the die, and it will automatically scale all the segments to fulfill this. You can try to do this. So now you'll see that he will change again. Yeah. Okay, so there are different ways of scaling the models, and yeah. So and this particular application is the one that is best illustrating this. Actually, there is a scaling tutorial, which is based on this particular model. And if you're interested in scaling, I would strongly recommend you to look into this tutorial. Okay, now we'll switch to another model to demonstrate the generic setup of the new body models. So for this purpose, we will choose the standing model. It takes a short while it's loading. So now you can see the model has been loaded, and you can see this model has no arms, and you can see here in the top of the main file we have, instead of this improvement that we saw before that we included the full body model, we now have two different files, and this is what is doing what that one file did previously. So we have this one file here called generic body model. And this file is basically a file that can automatically generate any kind of body part combination you may like, provided that it has access to this file here named body part setup. And in this body part setup, it's the one that I showed a part of in the slide. In this file, you can see that we have the trunk. It's equipped with the spindle muscles. We do not have a neck model right now. We have the right arm is disabled, but we can try to switch it in, and we can see that it would be, if this one here is present, then it would be equipped with spindle muscles, constant strength muscles. The left arm is not present, but we could take it back, and then right now we will not have any muscles there. We'll have only the moment generating muscles of the joints. Then if you go further down here to the leg, we can see this right leg is 0 and the left leg is 0, meaning that it's not using the old generation leg model, but it's actually, if you look further down here, the right leg TD is equal 1, meaning that it's using the Twente lower extremity leg for the right leg and as well for the left leg. But then if you look at the muscle configuration, you can see that there's difference in the muscle configuration. You can see that this right leg is using the simple muscles, whereas the left leg is using the free element muscles. And this is also reflected in this color change of the way that those muscles are currently displayed now. Okay, so now we switched on the two arms, and we can try to reload the model and see how it looks. Actually, one more thing about the standing model. It has also changed in the way that this particular model has also changed in the way that it's driven. If this has been the old standing model, then we would not have been allowed just to take away the arms and run the model immediately. We would also have needed to add or remove the drivers needed to specify the motion for this arm. But this particular application, the standing model, has been made generic so that it knows that if you take away the arm, I also need to take away the drivers for it, and if I add it back, I also need to get the drivers back, and so forth. So each limb has its own drivers defined, and it has been made generic in this way. So it makes it very easy to play around with different body part setup for this particular model. So now you see it appeared, and you can see that it really do have a right and a left arm now, and one of them with muscles, and the other one is without muscles. One of the other things that this model view can do is actually that you can also manipulate directly on this model view. That you can actually hide different parts if you like. So you can click on the items and hide them or make them transparent. So it became transparent there actually. It's maybe not so easy to see right on this one. We can try make this one here transparent. So now you see that the products became transparent. So you can do various manipulations directly in this model view, and it's our hope sort of to add more and more facilities that sort of makes it easy to interact with this model through the model view. Okay, the last thing I want to do a demo of is this selected output, and for this I'll load the bike model 3D, and I'll click this bike model 3D main. And now one of the new features of the system is also that it's asking you if you're changing if you open up a new main file and actually want to load that, try to load that, it's asking you if you really want to change that to shift to this file. Of course you say yes. One more thing, it's not just the standing model that has been made generic in the way that it can sort of that you can take on and off the different limbs and get rid of the drivers or get them back. Also, the free posture model can do set up in the exact same way. So so this is also a good model to play around with. So now our model disappeared out of the view, so we can click this icon here to get it back in the focus area. And we can try to run this application by clicking this one up here, run application, that it will actually calibrate the tendons of the muscles. It will start by calibrating all the tendons of the muscles, and then it will start running the model. It takes a short while before this has been finished. In the meantime, we can open up the chart view and start finding this graph. So we open up we click at the study, and we click at the output folder, and here we can find the model, and it always has the human model. And now in the human model, you will always find this selected output folder. And in this particular case, it contains the trunk, the right side, and the left side. And if you click at the right, it has only the leg, of course, because we have no arms. And the leg, it contains 3 different folders. It contains the joint reaction forces, the joint moment measures, and the muscles. yeah, but we have no data in there right now before this model has been finished. It takes a short while. So let's wait and see what we get. But it's, yeah, so this is really an attempt to make some of the most used data available. And if some of your users has requests for data that you would like to have available in this way, of course, it's such suggestions are very welcome. We can start looking at the results now. We can look at the joint reaction forces. You can see that we have in the hip, we have a hip medial lateral force, a hip proximal distal force, and a hip antero-posterior force. And we can click those curves individually and see the different graphs. And it's the same story for all the different joints in the legs that we have this available. Yeah, and actually some of this output, depending on what type of joint it is, it can also, of course, be moments. If for example, if it's a revolute joint, we have there are two moments available too in the knee. If you look at the joints, for example, we have the hip. We can look at the knee flexion moment. So this is the moment that the muscles generate around the knee. So this is summation of all the muscles spanning the knee, how this is add up to create the moment around the knee. And of course, as alternative sort of to read out directly the moment from the model would be normally just to run the model with no muscles, but having the moment generating muscles in the joints themselves. But this may not necessarily give you exactly the same curve, because there can be sort of different relations between the strength of the moment generating capabilities around the joint, depending on if you have this one moment generating muscles in the joint, or if you have a collection of real muscles spanning the joint. So it will not necessarily give you the same results, but it depends on the model. In some models it will give the same results if it's open chain models. Yeah. The last thing I want to show is the muscle envelope. Here you can see that for the right side we have this muscle activity envelope, meaning that there are no muscles on the right leg that has a higher muscle activation than this curve displays. And for example, if you wanted to see it for the left leg, we could put in a star here, and we will have also the left curve. Yeah. Yeah. So this is the output that has been made available in the selected output. So each body part would have its own file with where this is defined. So yeah, so there's a selected output.any file in each of the body parts where this is all defined. And in this file you will also see references to the coordinate system that has been used for measuring this. And of course it's a hope that we will at some point make it possible to display those coordinate system in a smart way in the model view, so that it's getting easier to interpret this output visually. Okay, I'll switch back to the presentation. Yeah, so now we've finished with the body parts and the demos, and look into the various, try to give a short overview of the various applications available. Yeah, so there is a bunch of new applications, and if you're trying to model a specific case, it's really normally a good idea to start with one of these applications as a basis for your model. And you can find all kinds of models here. Some of the news, I've just added some of the new stuff in the application are that there's a free posture model that is now made generic, as I told before, and there are these two GaitUniMiami models based on the Twente lower extremity model, and there's again the standing model which has been made generic, and there's also a new validation example actually. But you can also sort of try to divide these different applications into different categories, and this table is sort of tries to do that in a very crude way. but it's sort of attempt to make it easier for you to pick the right model for your particular application you want to build. So on this, in this column here, oops, I'll just switch on the pointer. In this column here, we have the different, some of the applications listed, and in the row here we have some characteristics. The characteristics could be that it's a full body model, that it's a model that is using friction, that it's a model that has conditional contact where it's not, you can actually define the boundary conditions which can shift in time. So for example, you can have the foot in the air, and then at some point it do really touch the surface of the ground, for example, and it can have a reaction force at that location. So there are if you want to do this particular model, it's a good idea, for example, to look at the conditional pedal model. If you're looking into market-driven models, gate models, then it's really that are making use of the Gait application 2 external application. Then it's really a good idea to look at the GaitUniMiami Twente TD model and the GaitUniMiami model. And if you're looking into models that are driven by driving the center of mass of a number of segments, it's a good idea to look into the standing model. So this is just an attempt to give a brief overview. It's not the full picture, but it's some of it. So one of the new applications is this GaitUniMiami model. It's running with a new leg. It's a variation of the previous model, and it has the motion of this model is being optimized using an external application named the Gait application 2, and it optimizes the marker location where is the marker located on the segment with respect to its local coordinate system. It's optimizing the segment length and joint axis to give the best possible match between to the recorded marker motion throughout the analysis. And this particular application in the repository, it displays the necessary steps needed to come from a C3D file to the finished inverse dynamic model. And it's currently a 15-step procedure. And it's not easy the first time you do this, but when you, as always, when you have tried it a few times, it works pretty well. Of course, we are working to reduce this number of steps and to make it easier, and we're doing this by implementing this functionality directly in the system. And this will make it easier this will make it much easier to do this kind of model in the future, we hope. And as I said, this model is also coming in a version with using only the right leg. To run this, to run a new, if you wanted to optimize using a new, if you have a new data set and you want to do a model on your own and you want to go through this procedure, you would need the latest release of this Gait application 2, and this can be found on this AnyScript community page forum, where there's a fourth section where you can find various files. I will show a short. I will show you this in a moment, and there's a link. There's a link here to this particular place where you can find this application. Yeah. So I'll just give a short demo of how to find this model, how to move around in this new community. So we have this new website, and it contains a lot of different information. Most importantly, I think, one of the most important things is that it, of course, contains a repository. So this replaces this is the new place to get the repository instead of the university page. This community is a joint project between the AnyBody research project at the university and AnyBody technology. And if you click on this repository, you will get a new site which is called AnyForce, and it's basically a place where we have defined a lot of various projects that contain releases of repository and models and so forth. And it's actually also, if you have a certain model that you want to share with other users, this is a good place to share it. And you can set up your own project easily and control who have access to your files. And really, it's a way of sharing the files, and you can have a wiki attached to your project. You can have its own forum and so forth. And you can have your own source control system, so you can work together with individuals and use source control through the site to share your files. So, for example, if we would like to find the newest version of this repository I've been talking about today, I will click this AnyBody Managed Model Repository, and it will jump me to a new site. This project site here, where you can see I have a short description here. It's very brief at the moment, and there's a documents section which contains some license terms about these models, and there's a file section where you can actually see the release of the repository as a zip file. Actually, I should say that this version 4 also contains already this particular zip file, but of course in the future it's not necessarily that will always be that new version of the system will always be in sync with the new repository releases. So this will be normally the place to find the newest release. Okay, and then one more thing about the site is that there's a snippet section which contains a number of small models that is not really sort of justify that you define them as a project, but it could be a model that sort of solves a small particular problem, and you want to share this model with other people, so you can actually upload this small self-contained model in this snippet location. Switch back to the main site here. There's also a wiki page, and in the wiki page there's a tips and tricks section. Lots of tips and tricks to see here, and there's a model troubleshooting page, and there's also a publication list. So and since this is a wiki and it's open for everyone, so if you have publications that have been based on an AnyBody simulation, you're most welcome to add your list of your publication in this list. So please just feel free to add the references here. There's actually also a small guide here to help you set up a project in the AnyForce. Yeah. And there is a FAQ, of course. Yeah. Then there's one of the last things I want to show is that there's a forum which is replacing the previous Yahoo forum, and this forum has a lot of new facilities which was not possible to do in the Yahoo forum. For example, one of the most important things that it's possible to divide the forum into different sections, sort of. So you can see right now we have 6 sections. And another important thing is that you can actually do attachment directly to the postings, which wasn't possible before. So it makes it much easier to keep track on the different files floating around. But of course, in this forum we also have all the old postings from the Yahoo, so they are all stored in the archive, and you can search them and so forth. Yeah. So if you haven't visited this community page, please visit it and join it if you find it useful. Yeah. And this one of the new things about this repository is that it comes with a new set of license terms. So we have now two versions of the license. The one I've been talking about today is the AnyBody Managed Model Repository. And there's also available on the AnyScript.org. There's also available the AnyBody Model Repository, which is basically the same models that were previously available at the university page. And these models are distributed on a very liberal terms named self-support license, and it corresponds pretty much, as I said, to the previous posted repositories. on the university page. The most important issue here is to consider that AnyBody technology will not put free manpower into supporting and developing these particular models. But of course, everyone is free to use the models with these terms. If you're looking into the AnyBody Managed Model Repository, it's also a free collection of models, and it's distributed under the terms named the professional license. And it's the model collection that the professional supporters at AnyBody Technology, they are investing their efforts in. And this works, as you have seen, this work strives to keep the models well structured and functional, adding validation examples, introducing new body parts, and make sure that all the parts are scalable, and introducing new applications, and introducing new user-friendly output, etc. The motivation behind all this and this division, you can read all about that at this link here. So thank you for your attention, and please feel free to